lecture 7.2, wave interference. The overall view of this lecture here is that we first want to start off with understanding the basics of constructive and destructive interference. However, part 2, wave interference due to path difference, this is by far the most important piece. So that's really what we need to really explain to the best of my ability here. Constructive and destructive interference. I am assuming that you have already seen this in your introductory mechanics course. So I will go through this somewhat brief. As we just derived in the previous section, the previous lecture, interfering wave amplitudes vary according to the phase value. They can increase, decrease, and even neutralize themselves. We focus on the two maximal interference patterns. We have maximal amplitudes maximal amplitude patterns are called constructive Well, if I have zero amplitude patterns are called destructive. Now note that there are other values that we can have, but those are the two that we primarily focus on. We will focus on the values of the phase or when constructive / destructive occurs. From superposition, we found that if we have two waves, let's call this wave wave 1, which was A sine of kx minus omega 2. And if we had a different wave, y2, which would be a sine of kx minus omega t, and we had some phase factor that if we combine these waves, we saw here is that the resultant wave was a combination of adding this wave to that wave, and we ended up with the result that read twice the amplitude of cosine of 1/2 phi times sine of kx minus omega t plus a phase of 1/2 a phi, where the effective amplitude of this wave is then 2a cosine of 1/2 phi. So for us, this becomes the central thing that we look at. So let's go look at this thing here. So the first thing that we want to look is that we want to look at, I'm going to start off with what is called maximal destructive interference. Maximal destructive implies that the amplitude of the superimposed waves is 0. So then we have to ask the question, for what values of the phase phi is this true? Well, it has to be where cosine of 1/2 phi is 0. So the answer is when cosine of 1/2 phi is equal to 0. That means the only place where that can be the case here is that I have to have odd multiples of pi. So if I set phi here, so this implies then that phi is then going to be plus or minus pi, plus or minus 3 pi, because that's going to give me 1/2 pi, which is 0. The next one's going to give me 3/2 pi, which is 0. So you can see here is that it's the odd multiples. So then this will be the odd multiples of pi. So if I want to see destructive interference, the amplitude is 0, I have to choose odd multiples of pi for the phi. Now note, this guy, the first value, is typically called the principal value. And it's typically plus pi. It's just convention. So what does this mean? So if this is the case, here's what we find. Two waves that differ by phi equal to pi, which is 180 degrees, are said to be out of phase relative to each other. So if I look at the waves here, let's imagine that this here is my starting point. So what that means here is that one wave is going up, and this wave is moving this way. Remember, it has to be a traveling wave. And then the other wave is in the opposite direction. It's out of phase by pi. So what I mean by pi here is that if you look here, this distance between here and here for the wave, this is exactly pi. And again, this wave is moving to the right. It's a traveling wave. So what this tells me here is that if I now look at the amplitude, right? The amplitude, which is now 2a cosine of 1/2 pi, which is 90 degrees, is then going to be 2a cosine of 90 degrees, which we know is 0. But the intensity is equal to the amplitude squared. So this tells me here is that now its intensity is exactly 0. In other words, this phase of odd multiples of pi will always give me a 0 amplitude. So if I redraw this again, we can look at this in terms of a picture. Because if I have a wave going up and down like this, and then I have my other wave going up and down like this, we can see here that a portion, the green wave, when it's down or up, the red wave is doing just the opposite. In other words, it's exactly out of phase. And as a consequence, this tells me here that I'm now going to have a 0 amplitude. That looks like this. Now, to show this, I want to look at a Duffy wave interference applet. And remember, all of these are in the lecture links. And they're all in the lecture links. So what I'm going to do here is that I want to go and share my screen. Wait, give me a second here. And okay, so if you look at this, what I'm going to do here is that I'm going to reset this. Okay. And what you're seeing here is that, look what happens. Look at the red wave. They're moving towards each other. Now look, they have not started interfering. When interference starts here is when these two waves are at the exact same place and time. So now if I start to step through this thing, oops, you know what I did? I'm doing constructive. I need to change this. And then let's try this again. So you can see here that the red wave is in phase, I should say. It has no phase. The blue wave traveling to the left has a phase of pi, or 90 degrees, excuse me, 1/2 pi. So as they come in, what you're seeing here is that these guys do not start to interfere until they're right on top of each other. So now if I step through this thing, what you're going to see here, oh, this is taking longer than what I expected. You could see that when they're exactly at the same place at the same time, the amplitude is 0. Now, another thing that this word interfere is a misnomer, because look what happens to the waves. Interference typically means like you're interfering, you're blocking something, but check this out. If I just play it, you could see that the waves afterwards do not change shape whatsoever. But destructive interference occurs for just a brief moment here. So what I want to do here is that I want to come back and I want to show you. So I made copies of this thing, of the Duffy applet, and I want to show you this. And so there's a couple of things that we want to look at. Again, so here, what we're seeing here is that they're going to start to interfere. And then here, what we're seeing here is they're at the same place and time, which means that they're now interfering. And what's the important piece here is that note that the waves keep their shapes even after interfering with each other. Therefore, interference is really a misnomer, right? Because sometimes we'll say, hey, this person is interfering, and they're sort of like obstructing. That is not the case with wave interference. Now, let's move on to constructive interference. Maximal constructive interference. Maximal constructive occurs when cosine of 1/2 phi is maximal in value. Question: for what values of the phase phi is this true? And of course, the answer is when cosine of 1/2 phi has to equal plus or minus 1. That's when it's at maximal. The only place that could be true here is if cosine is equal to multiples of even pi's. So in other words, phi can either be 0, plus or minus 2 pi, plus or minus 4 pi. And we could see here is that this has to be even multiples of pi, including 0. So if I look at this, 0 is typically called the principal value, or we could have used 2 pi or minus 2 pi, but this is the principal value, and that's what we'll show here. So if I move this up a tiny bit, here's what we're going to see. 2 waves whose phase is 0 are said to be in phase. They're marching together in phase relative to each other. So another way of saying that these waves are, so the waves are in sync. So if I look at this, you could imagine that I have a wave, my red wave, and this wave is traveling to the right. Then my second wave is also traveling to the right, and they're at the same place and at the same time, like this here. This tells us then that the amplitude which is now going to be 2a cosine of 1/2 of 0, then gives me a value of 2a. So this implies then that the intensity of this wave is 4a squared. So picture-wise, what I'm seeing here is that if I look at this thing again, right, if I take this thing and I copy it and I put it down here, so if this is my wave here, when they superimpose, the wave, the resultant wave, is then going to be twice as high. Now the intensity is the square of this thing, so it now makes this 4 times more intense than if a single wave. But let's not look at this right now. Let's go to the applet to actually look at this thing. So here we go. So what you're seeing here is that, let me change the wave. So I'm going to go to constructive interference. So look at the waves. They're coming in, and now they're going to start to interfere. As they start to interfere, they're overlapping, and you can see here is that the amplitude goes from 1 square. Look at the red and the blue square. They go from 1 square to 2 squares. They have doubled their amplitude. And then if I allow that to keep going, you could see that constructive interference only occurs for a brief moment. Let's look at this one more time. So if I now go back and I share my screen of what we just saw, here's what we're looking at. So let me grab the image that I have. And again, this is the Duffy wave interference applet. And you could see here is that this right here represent constructive interference. So in other words, one more time, that at a single place and time, these two waves behave as one. Now, this result that I just stated up here is really surprising. It's surprising because the intensity depends on the amplitude squared. So let's look at this thing. Okay. So I'm saying that this is surprising because superposition of two waves results in a single wave with an amplitude, not an amplitude, an intensity four times higher. I mean, this is a pretty shocking result, and I'll show you why that is. So if I look at the intensity here, so let me try to adjust my, let's say that I'm going to set my bottom here. And then I'm going to set this guy right here. So what I have here is that this is the intensity of a single wave. And this guy should be a squared. And I should have cosine squared of 1/2 phi. Oh, no. There's no phase. It's just a squared, right? It's a squared. And it should be sine of kx minus this guy right here. So if I look at this guy, my intensity looks something like this. It's going to oscillate up and down because it's sine of squared. And what you're seeing here, that this guy, again, is for a single wave. And we could see here is that these are the intensities right here. And the key thing here is that this guy is just a squared, maximum height. Now, what I want to do here is that I want to compare this to an intensity for superpositioned waves. And this guy is going to be for a squared sine of kx minus omega t plus 1/2 phi. So if I look at this intensity, it's not 1 times, it's not double, but it's 4 times higher. Right? That is quite a big difference here. So if we were talking about light, light would be 4 times more intense, not twice. So in this case here, you're seeing here that this height right here is 4a squared. And this is for 2 interfering waves. So why does this occur? Why is the intensity 4 times larger than a single wave? And it turns out that it's a little bit slippery, but this is the answer. It says that the process of interference moves energy from destructive areas into constructive areas. It does not violate conservation of energy. We will talk about this more a little bit later here, but I did want to show you one more applet, which I think is quite good here, and it's going to look something like this here. So what I'm going to, this one is by this German guy, super nice guy, Fendt standing wave applet. And I want to make sure that this is really clear. I'm a little bit hesitant to show you this applet because standing waves are not waves, but oscillators. It's an oscillator, not a standing wave. But the reason why I'm going to show you is because we can see very, very clearly how we have interference. And the images that he produces are quite beautiful. So let me go here. And what you're seeing here is that here's this applet. Remember, this is superposition, and it says a reflected wave, but remember, it's still a standing wave. Okay, so check this out. It moves very slow. So here it goes. So here's the wave coming in. Now it's going to reflect, causing a wave to move in the opposite direction here. And you can see here is that these waves have regions of constructive. This, okay, I'm going to move slow here. Right? That's constructive interference. They're in the same location here. And then they can also have destructive interference. And you could see here that they will be out of phase right here. Okay, that's completely out of phase. So now what I'm going to do is I'm going to let them run. And here we go. So you see constant in phase, out of phase, but what I want to show you here is the resulting waves. And so I'll stop it when they get to the peak of constructive. And you can see that right there is constructive interference. They're in phase, but this little dotted wave is the resultant wave. And you can see that it's twice the peak. And if I continue, we could look at destructive. Oh my, this is really slow. It's beautiful though. And you could see right there pretty close that that's destructive. So if I go back to my screen, what you're going to see here is that I have waves that are coming in. And here's when I have regions of constructive interference. And if now I add the resultant wave, it now looks something like this. So if I was to look at this, maybe label this a little bit better, I could say that this is the wave Y1. This is the wave Y2. And so when I look at this wave up here, this is Y1 plus Y2. And you could see here is that these waves right here, these are the resultant wave with twice the amplitude. But at the same time, I can also have destructive waves. So if I look at this situation, this here tells me that I have two waves. I have a wave traveling in this direction, and now I have a second wave that's traveling in the opposite direction. And so you're getting this interference where I now have destructive interference. And then if I look at the resultant wave again, I have this image that looks something like this. And you could see here is that that black line represents the resultant wave with zero amplitude. Now again, that black line right there is Y1 plus Y2.